Have you ever wondered what literally holds our modern world together? Well, it's welding. It's this powerful, precise art of joining metal, and it's the hidden secret behind, well, everything, from towering skyscrapers to the life-saving tools in an operating room. So let's dive in and see how it's done.
I mean, really think about it for a second. You look at a car, a bridge, a massive ship, and it all just looks like one solid piece of metal. But of course, it's not. So, how in the world do you join two pieces of steel so perfectly that the seam actually becomes stronger than the metal around it? The answer is this amazing process that's both ancient in its concept and just unbelievably futuristic in how we do it today.
At its core, the principle is called fusion welding, and it's actually brilliantly simple. You take intense, focused heat, you point it at the edges of two pieces of metal until they turn to liquid, and you let them flow together into one molten pool. Then, as that pool cools down and gets solid again, the atoms from both pieces just mingle and lock together, making them one. The real genius, though, is in how we create that heat. We're going to start with the classic, the original powerhouse of modern welding, oxy-fuel welding, or OFW for short. This is really where the story of building big things out of metal takes off, and it all starts with the most basic tool there is, fire. So how does it work? Well, it's super clever. The torch itself is this precision instrument that takes a fuel gas, acetylene is the most famous one, and then blasts it with pure oxygen. What you get isn't just a regular fire. It's this incredibly energetic, super focused flame that can create a puddle of molten steel in just a few seconds. And when I say intense, I am not kidding. An oxyacetylene flame can burn at up to 6,300 degrees Fahrenheit. Just to put that in perspective, that's more than double the temperature you need to melt steel. It's actually hotter than the surface of some stars. And all of that power is right there, perfectly controlled at the tip of a handheld torch. So you've got this combination of raw power and fine control, which made oxy-fuel welding the ultimate industrial workhorse. And because the gear, basically just two tanks of gas and a torch, is so portable, you could take it absolutely anywhere. That made it essential for building and maintaining the very backbone of our modern world. Yeah, that portability is just a huge deal for heavy-duty work. I mean, think about it. Repairing a crack on a giant piece of mining equipment, or welding the pipelines that carry our energy, or maintaining hundreds of miles of railroad track. You can't bring those things into a shop, right? Oxy-fuel welding goes to them. It's the go-to for critical repairs out in the field. But here's what's so fascinating about oxy-fuel welding. That exact same raw, almost destructive flame, well, when you dial it down and handle it with some skill, it completely transforms. It becomes this delicate tool for artists and high-precision fabricators. It's honestly incredible to think about. The very same process that's used to fix a rugged railroad track is also used to create these beautiful, delicate metal sculptures, or to perfectly weld the thin sheet metal on a car body. That incredible range, from heavy industry to fine art, that's what makes the controlled flame such an enduring technology. But for all its versatility, a flame has its limits. The heat spreads out and that can warp thin materials. And it's not always precise enough for tiny microscopic jobs. So to solve that problem, we had to move beyond fire. We had to leap from the very visible, tangible world of flame into a new era of invisible, highly focused beams of pure energy. And there are two main players in this advanced field: laser beam welding, or LBW, and electron beam welding, EBW. Now, as you can probably guess from the names, one uses a super concentrated beam of light, a laser, to melt the metal, while the other uses a high-speed stream of tiny particles, electrons. So we're talking light versus particles. But what does that mean in the real world? Okay, that's a cool distinction for a physics class, but what does it actually mean on the factory floor? Like, when would you choose a beam of light over a stream of electrons to join two pieces of metal? Well, it's the applications where the differences become totally crystal clear. This chart just lays it out perfectly. On the laser beam side, you see things like thin car body panels, delicate little sensors, surgical instruments. Lasers are amazing at delivering precise energy right to the surface without a lot of extra heat spreading around, which is perfect for high-speed work on thin or heat-sensitive parts. Now look over at the electron beam column. Thick gears, jet engine turbine blades, even nuclear reactor vessels. Whoa! Because electrons are actual particles with mass, they physically burrow deep into the metal, creating this incredibly narrow, super strong weld in thick materials where failure is just not an option. So, from a simple flame all the way to a focused beam of electrons, what's the big picture here? It's that these processes are the invisible architects of the world you live in every single day, often in ways you would never, ever expect.
Really, the best way to think about these isn't as competing technologies, but as a specialized toolkit. You've got oxyfuel welding, that's your rugged, portable all-rounder. You've got laser beam welding, that's your fast, precise specialist for all the delicate jobs. And then you have electron beam welding, the deep penetration powerhouse for the most critical, high-strength parts.
And that, right there, is why this all matters. The perfect, seamless fit of your car door. The mind-boggling reliability of a jet engine turbine blade spinning thousands of times a minute. The safety of a medical implant inside a human body. All of these modern marvels depend completely on someone choosing the exact right weld for the job.
So, from the raw power of fire to the pinpoint precision of electrons, these are the technologies that literally fuse our world together. They operate at this fundamental atomic level to build our entire civilization. It just makes you wonder, what's next? What invisible force are we going to harness to build the world of tomorrow?